This is lesson 1-2 on the composition of functions. We'll discuss also the combination of functions, which is extremely easy. So as you can see here, this is all in function notation. This right here would be the f plus g of x. And to evaluate that, you simply need to find f of x and g of x and add them together. Similarly, for f minus g of x, you find f of x and you subtract from that g of x. F times g of x is the product of f of x and g of x, and f divided by g of x is f of x over g of x. This presents an interesting case. We cannot let g of x equal 0 because that would mean we're dividing by 0. Okay, so for example, let's say that f of x is 3x plus 1 and g of x is 1 minus x squared. We can actually compute these without much difficulty. As you can see up here, f plus g of x is just the f of x plus g of x. Well, we know that f of x is 3x plus 1. If you find it helpful, you might put the originals in parentheses, plus g of x, which is 1 minus x squared. And in this case, we simply have to combine like terms. There's only one x squared. There's only one x, and there are two constant terms. 1 plus 1 is 2. It works very similarly for subtraction. F of x minus g of x. Okay, and again, we do this the same way. We'll need to distribute this negative. When I'm looking for the x squared terms, I have minus negative, so it's positive x squared. There's only a 3x. And here I have 1 minus 1, which is 0. That's that. For f times g of x, again, you'll see why now it's helpful to have this in parentheses. F of x times g of x. These are two binomials. To multiply this, we'll need to use the FOIL method. First times first is 3x. The outside terms is going to be minus 3x cubed. The inside terms is going to be plus 1. And the last terms minus x squared. If you'd like, you can rearrange these in descending order of degree, but I'm not going to bother. And then finally, for f of x over g of x, I'll simply write this as 3x plus 1 over 1 minus x squared. Okay, feel free to leave f over g of x in this form, but we need to remember this domain restriction. We cannot let g of x, we cannot let what's on the bottom here equal 0. So to figure out when that's equal to 0, I'm just going to go over here to the side. I'm going to set 1 minus x squared equal to 0. You can either factor this as a difference of squares, or you can add x squared to both sides and take the square root. I'm going to factor 1 plus x times 1 minus x. And so if x is equal to negative 1 or positive 1, then g of x is equal to 0. That's a problem. I cannot have this denominator equal 0. So this is f of x over g of x, but I need to state that x cannot equal positive 1 or negative 1. Okay. And now composition of functions. This one's slightly more complicated. Perhaps you've seen it in previous math courses. Essentially, a composition of functions is when we perform one function on a number, and then whatever number we have when we're done, we give that to another function. So it's essentially one function and then another. I've tried to capture that in this illustration here. To get f of g of x, I have to start with x. I stick it into g of x, and whatever that spits out, I feed to f of x, and what that spits out is the composition of functions. The way that we write this, we either write f of g of x, or we write it this way with an open circle there. I prefer writing it this way. Whenever I see it like this, the first thing I do is rewrite it like that. Let's look at examples, and hopefully that'll clear up any confusion you might have. Okay, so it says f of x is this, g of x is this. Find f of g of x. Okay, well, again, as I just said, I always rewrite it as f of g of x. I rewrite it this way because it makes more sense to me. Okay, To evaluate this, the first thing I need to start on the inside. I need to evaluate g of x first. So essentially, f is stuck waiting while I evaluate g of x. Now, they told us that g of x is 3x squared plus 1. If you look at the illustration here, I can imagine sticking x into g, and after I stick x into g, I'm left with 3x squared plus 1. And now I'm going to feed that to f. When I feed an x to f, it says 6 minus whatever you feed me. So if I'm feeding it this, it's going to spit out 6 minus 6 minus what you fed it. Okay, hopefully you can see that with the illustration. If not, I'm gonna work it the way that we typically would. So f is waiting outside. G of x is it's exactly 3x squared plus 1. They told us how to find g of x. And now I'm going to evaluate f at this crazy number right here. Well, all I have to do is plug this quantity in for x, because I'm replacing it here, so I replace it here. So it's going to be 6 minus, instead of x, I'm going to write this quantity. And it's easier if you write it in parentheses. Okay, we're going to combine like terms. There's only one x squared. There's only one quadratic term. There are no linear terms, and our constants, 6 minus 1 is going to be 5. That's how we find the composition of functions. With these same two, I'm going to find g of f of x. Let's see if that's the same thing. We're going to work it backwards. I'm going to immediately rewrite this as g of f of x. Again, this time, f of x is on the inside, so it goes first. G waits patiently outside. F of x is 6 minus x. And now it's time to evaluate g, but instead of evaluating at x, I'm evaluating it at 6 minus x. So to find that, I'm going to replace this x with 6 minus x. So it's going to be 3, and I'm going to put in parentheses 6 minus x squared plus 1. Okay, and you'll need to FOIL. 6 times 6 is 36, times 3 is 108. And then I have minus 6x minus another 6x. That's minus 12x times 3 is minus 36x. Minus x times minus x is plus x squared, so we've got plus 3x squared, and then the plus 1, which is right there. If I rearrange this, I get 3x squared minus 36x plus 109. Okay, and that's how that's done. Now, g of f of 2. There's two ways to do this. We can simply evaluate f of 2. G waits patiently, and f of 2. Well, 6 minus 2 is 4. And then evaluate g of 4. So we're going to plug in 4 here. 3 times 4 squared plus 1 is 49. We can do it that way, or we just found out that this is what g of f of x is equal to. So we can say g of f of 2 is equal to this, and I'm just going to plug in a 2. So that's 12 minus 72 is negative 60. Negative 60 plus 109 is 49. Either one of these ways work. Composition of functions. Okay, so we're going to build a composite function in this case, and when we're done, we need to find the domain for f of g of x. Well, let's go ahead and find f of g of x. Because g is on the inside, it goes first, so f is waiting patiently outside. G of x is the square root of x. And now I'm going to plug this in into f of x. So it's 3, and when I get to an x, I'm going to replace it with the square root of x. Again, I typically write these in parentheses. And then I square it and add 2. 3 times, well, the square root of x squared is simply x plus 2, and we're done. Okay, so f of g of x is 3x plus 2. We have to find the domain. Well, if you were just to look at 3x plus 2, you might say to yourself, it's a linear function. Any x will do. But there's a problem. We started with g of x, and not just any x will do in this case. In fact, any negative number is going to mess up g of x. You cannot take the square root of a negative. It has to be at least 0. So for the domain restriction, this is f of g of x, but I need to add that x has to be greater than or equal to 0. Otherwise, it's going to foul up f of g of x, the composite function.